Hi, chat. Can you tell me if you are seeing something other than just a black screen? That's the camera, but all I'm seeing on the YouTube copy of the stream is a black screen. And I'm wondering if you're seeing something different.
Are you streaming right now?
Yes. Also copy it to YouTube so that I have it on my record so I can use it.
Did you post the YouTube link?
I'll make a playlist with all of them so that you have them. It's not a matter for this year because you have all the
Yeah.
Zoom file. Oh. Black screen. Okay. There. Oh, resume share. Okay, have to separately resume the share. That fix it? I'm still, yes, okay. Oh, I forgot to download my files. So last time we had finished with some rotations of stress tensors, if I recall correctly. So that should give you the basics for working on your paper, going through your literature review. Today, we're studying a part of actual implementations and having fun. I mean, we did have a little bit of fun last time, but this is where we start into the real fun of using spreadsheets with our numerical methods. So we are going to introduce the finite difference method. And the finite difference method is based on the truncated Taylor series expansions of approximation of functions by differential equations. And basically, the slope of the first derivative of a function can be approximated by the delta equation. So the delta y over delta x, the slope basically of the equation. We're going to use that for the basis of our calculations. So let's say we want to solve an equation, a differential equation, first of all. So let's start with an equation that we're going to differentiate, express it as a derivative, just to get an idea of the feel of how the process works, right? So if I were to say that the differential equation of that is simple equation, quadratic equation I have is a straight line. So if I express it as a differential equation, then first derivative is just a straight line because it was a parabola. And so I can express that same parabola as a difference equation. I say that delta x over delta x, delta y over delta x at any point is approximately equal to 8 times x plus 5. Approximately, because obviously we're averaging out, we're assuming a straight line where it is not. And so it is not equal to that. And you can always go to the expanded Taylor series to have more terms, but always the first term for the first degree derivative is the most important component. So we have that value. So what do we get if we have that difference equation? Well, I have delta y, okay, is equal to I can multiply 8x plus 5 by delta x, and now I have expressed my delta y as 8x plus 5 times delta x, right? And if I detail, so here I'm assuming that I have a constant interval in x, right? Because I could have all kind of delta x's. Right? So if I have my x-axis, in this particular case, we're assuming that we have a constant interval along that x-axis. So whatever my interval is, I'm assuming that I have a constant interval. It doesn't have to be, okay? So I can express it as something more complex than just a constant interval. But what is the advantage of expressing it as a constant interval? What do you think? So why would I want, whenever possible, to express it as a constant interval, the delta x? Yeah.
You can discretize it over the entire delta x.
Well, you could do it even if it's a variable interval. See, my x's, they could be spread out. They don't have to be, oops, like this, right? I could have had my x's, I mean, I find the delta x is just the difference between two consecutive x is, but they could be variable distances. They don't have to be the same. Okay, they're just the points at which I will evaluate. So what's the advantage of having it as a constant interval? So if it's not a constant interval, so look what I'm doing here with my y. I express delta y is y at node I minus, so the difference between, so two consecutive points. If I was to use variable interval, I would also have to do the same thing. So I would have to look at their coordinates, their values of x. So this is a constant value. I can factor it out. It will be the same for all values, so I can multiply it once at the appropriate location. Okay, so in terms of computational steps, it will save me because if I had two terms here, it would be xi times 8x plus 5 times xi plus 5 times x I minus 1, etc., etc. So it complicates things if it's, I mean, you can express it, obviously you can do it. It's not very complicated. It's not highly complex, but it does add at each step computational complexity. So sometimes it's more convenient to use a constant one. When would it not be when would it be better to have a variable mesh?
Either at boundaries or loading, different loading.
Yeah, when you have a domain where you're going to have a lot of changes in an area, but it's fairly constant elsewhere, there's no need to go through the additional complexity of evaluating everywhere in a very dense mesh when you can have a coarser mesh when you don't need the extra resolution. So there's reasons to prefer it one way or the other. But whenever possible, we like to use a constant value simply because it makes it easier to evaluate, to express it in terms of formula, but also it makes it easier to process, less time consuming, less resource consuming. Okay. And so we end up with an expression of the form, say, y to the I is approximately equal to 8x plus 5 times delta x. So if I want, my next step is yi, or I could call this yi plus 1 and this yi, whatever. Notation can be relative. So this is the backward, this is the backward slope. So there you can do forward, but backward is the simplest because you know the previous value, so you calculate from there. If you go forward difference, then you pretty much have to store things and solve a matrix at the end. So the backward difference allows you to propagate things from known initial conditions to future conditions without necessarily solving a matrix. So when I mean, you can still solve the matrix, but when you want to use less memory, because remember, the matrix in all these operations is a square matrix. So however many nodes you have to square. That's the memory requirement. However, when you don't solve it through matrix, you are using more processing, because sometimes you want to approximate in between and you do it in multiple steps. And even at steady state, I mean, if you're doing something that is time dependent, you will have to do it step by step anyways. But if you're doing it at steady state, the conditions, you could in theory solve everything at once by building a matrix. But of course, you need the square of the RAM, right? While when you do it step by step, you need at most twice the amount of memory from the number of nodes, one to store the previous step and then the next step if need be, depending on how you do it. So there are these requirements where you can exchange time for memory or memory for time. So let's go through back to the initial equation. Let's see, we have 4x² plus 5x. Let us start a spreadsheet based on that. So we said that our equation was, forget it already. 4x² plus 5x minus 2. Plus 5x minus 2. So this is the equation. We can have a set of points. So, that's one. So let's go step 1. And we have 4 times x. Or a better thing we can do is define this as x. Then we can say simply 4 times x squared plus 5x minus 2. For x squared plus 5x minus 2. And we wanted to say is equal x 8x plus 5 times delta x plus 1. So delta x is 1 in this case. So 8 times x plus 5 and delta x plus the previous one, right? So the key thing is previous. And we have not defined delta x. I'm just going to define it now. Delta x is 1. Public E x. There you go. The thing is, we need an initial value, otherwise it's not valid, right? So it always depends on the previous value. Okay, and that's what we must do here. If I were to do forward difference, I would obviously have to start from the end. If I knew the value at the very end, but if I only know the value before, then it's more complicated. The thing is, yes,
You mentioned forward difference. How do you know forward difference when it's?
well, in this particular case, you would not have to know for what range, right? Whether it's forward or backward difference, I need to know the domain. X is my domain from 0 to 10. That is the geometry. Determines it. Forward difference would be, I mean, you'd have to set up your relationship between each point. Right? And so depending on how you started or where you start from is how you would know it. Okay. So as you increase, but one thing that you can see here is that if I use an interval of 1, and if I use an interval of 0.1, the difference between the error becomes increasingly negligible compared to the real thing. So one of the solutions to increase your accuracy is to decrease your interval, and you will increase your accuracy. Obviously, it increases computation time and memory usage and everything. So you have to take that into consideration. Now, we don't solve simple equations like that typically. In numerical method in geotechnical engineering, we are usually considering cases of seepage, consolidation, often heat fusion, contaminant transport, or some people will do everything together, right? So, because you can mix these, there's many sets of equations. You can then couple the equations themselves, have more complicated terms to couple them at once. You can do pseudo coupling by having many intermediate time steps and calculating each one, taking the output of each one that is required to calculate some values in the next. So for instance, heat transfer depends on seepage, because as you have seepage, you have movement of say of water at a given temperature. Depending on your heat conditions, that heat has moved. So you calculate the heat diffusion. It controls the water temperature here, but now you're moving it because of the seepage, and that affects at the next step the heat calculations, because you're moving the water at the same time. So the same thing with contaminant transport and so on. You also change the viscosity of water, which means that the hydraulic conductivity may change. So things like consolidation rates may change also due to these things that can affect each other. So if you don't couple, typically you need to go more refined in terms of time steps to be able to achieve what you get from coupling. But the mathematics is usually easier to implement. So we're not going to go in depth in those things in this class. We just show the basics. So you use obviously seepage as a finite difference. It's an easy way to get these nice figures. I'm sure you remember from undergrad, right? The seepage, the flow nets that you had to draw by hand. And yes, the the drafting table before the advent of digital computer was an analog computer that people used all the time. By following the rules of scaling, by following the rules of keeping the angles 90 degrees and so on in the drafting table, you were able to reach an approximate solution, which was within the range of accuracy of the method within the scale of your drawing and so on. So if you were to do it by hand like this and you compare your result to a numerical solution, you would probably get comparable values given the error in actual measurements of material properties is much larger. The difference is, of course, that it's much easier to accommodate very diverse soils when you're dealing with numerical methods, right? When you do it by hand, if you have horizontal layers, then you can scale differently depending on the relative hydraulic conductivity, say, of each layer to do your flow nets, as you may recall. So you could always scale things like that. But if you have little lenses of things inserted here and there, then it's just impossible to do. So it was a good approximate solution, but it becomes very difficult to handle complex scenarios, which is where numerical methods come real handy. So everything starts from Darcy's law. And in Darcy's law, basically, we're gonna think of it first in 1D, simpler to picture where the law comes from. So you may recall that the flow of Q is the instantaneous discharge in meter cube per second. Okay? So you have a volume of water that goes through an element of soil. In this case, it's a linear element, which has a cross-sectional area A. So the cross-sectional area of the I should have that dialog box on my screen there. Mouse pointer expand. I just wanted to have the equivalent of the laser pointer, but let's just show here the oops. So we have here the cross-sectional area as of that disk. So we imagine an element of soil has a volume, but in that volume where the water flows, we have the cross-sectional area A. We have the intrinsic permeability K, lowercase k. That's the intrinsic permeability. In geotechnical books, literature, sometimes you will see that hydraulic conductivity is called permeability, but it's a function of the viscosity and the density of the fluid. Okay, so here we will, for the class, we will really separate hydraulic conductivity because it's what it's called in any other field of science and earth sciences. Okay, so we will keep permeability at lowercase k, and to refer strictly to permeability, which is only a geometric function of the soil. Okay? While hydraulic conductivity is a function of the fluid. So the density and the viscosity of the fluid with the solid medium, that affects the hydraulic conductivity. Okay? So we have a gradient of pressure. So the difference of pressure between the entry point and the exit point, that's delta P. and the difference in length, so the length of the element of soil is delta L. So you may remember, I'm sure that you do. Everyone remembers that Darcy law is minus K, where capital K is hydraulic conductivity in this case. So the pressure, pore pressure has disappeared and it's become the change in height. So height of a column of water. That's why the unit weight of water goes into hydraulic conductivity. So we took out gamma divided by, so we have basically gamma times delta H is with delta P. So we took out gamma multiplied by K divided by mu and also divide by A because here we have capital Q while the Darcy flux is lowercase q, which is Q, big Q over A. So this is the flow per square meter of area. Okay. Some people will call it velocity. It's not the velocity, okay? It's not the speed of water, it's the apparent speed of water. If you look at the water coming in and going out, that's about as fast as it moves across, but the real velocity will be higher because it's doing all kinds of tortuous paths. Okay? But as a line across in the direction of the gradient, that's the overall apparent velocity that water has going through. Okay, so properly called the Darcy flux. So minus K, why minus? Because it goes from an area of high pressure to an area of low pressure, right? So because it goes down the gradient, that's why we have a negative. So minus K times the difference in pressure head. So pressure expressed as the difference in height of water. That's what delta H is over the length over which it happens. And so that's all that Darcy flux is. And it's a very simple linear relationship. Now that's one in one direction. Now we were using a difference in this case, but I mean, if you're going infinitesimally small, you're really going to define it as a differential. And it is a vector because that was in one direction. So if you have a difference in pressure between this point and that point, it pushes that way. But at that point, there might be another pressure, so it may also point towards that way, and somewhere in between will be the effective angle, and that's in 3D. So the actual Darcy flux is a vector value. That's reflected, it should be, oops, that's a mistake. What should I have done with that? With the value Q, what should it look like in this equation? I made a mistake based on the statements I made to you last few weeks.
I have plot. Plot.
Yeah, it should be bold or it should have a little arrow on top, right? Or it should be bold like I, J, and K because it does have a direction, okay? It is not a scalar value. Okay? And typically we will indicate it with either an arrow or making it bold. So Q is a vector and it depends on the hydraulic conductivity in each direction, which may differ between each other, okay? So you don't always have the same hydraulic conductivity in each direction. So do you remember how we represented, what do we call this? The function that converts these H into Q? We gave it a name a couple of weeks ago. This is called a gradient, right? So we have the gradient represented by the Nabla operator. So we can simply write that whole equation is exactly this, okay? This is exactly the same equation, okay? Minus K, which is a scalar, and Nabla of H, which is a number field. scalar field, H. So notation wise, it's exactly the same. Now, when we consider changes in water content though, what is the change of water content in a volume of soil, of porous medium? Again, we start with looking things in one direction. Okay? We're not going to look at all the direction, but the change in water content over time, since the Darcy flux is the movement of water over time. So we have a flow coming in, minus flow coming out over an element over a length of soil, okay, will give us the change in volume basically over time. And so that is, you can just express it as minus delta Q over delta L. So again, if you express that in terms of differential notation, you will have minus dk dH over dl over dl. You will see this equation often represented this way or with differential equations, but in this manner. That assumes that K is constant in a medium, okay? So if you have constant value for K for hydraulic conductivity, this is a good way. You see you will see this equation also for heat conduction. But remember that if K is variable or the heat diffusion is variable, K should be inside the operator here, okay? Because you will have different K values for different terms. So this is what it really represents. This assumes a medium with a constant value. But as soon as you get to the boundary between two values, you have to be aware that this is the proper notation. Now, there's different ways of looking at it, either through the central difference. There's different ways you can represent your difference terms, right? We said the backward difference, the forward difference, or the central difference. Usually the central difference is more accurate. And let's see why that is. So if I have a curve that is nonlinear, let's say that I have two points along that curve. Now, if I do the forward difference or backward difference, I'm basically I do the difference, sorry, between these 2 points. If I find the slight slope by saying delta H over delta Y over delta X, that's basically the slope between the 2 points, correct? Now, if I were to look at the slope at this point, it looks like this. The slope at this point, it looks like that, right? If I look at the tangent. And as you can see, these 2 points are very different to each other. Okay. So if I'm trying to determine what the slope by the difference between 2 points, should I assign the slope to this point or to that point? Neither. However, if I look at a point exactly in the middle, exactly in the middle will be somewhere there. Okay, so it may not be very exact, but well, let's go with that for now. It's good enough for now. If I go and take a slope here that is tangent to the line at this point, right? This one is much closer to that point. And if you have a second degree curve, it will always be exactly equal to the slope at the midpoint. So if it's a second degree curve, at the midpoint, it will always be close. But whatever curve you have, if it's a continuous curve that doesn't change curvature in the middle of the interval, you will always get a slope which is compatible. So the difference between 2 points is more compatible with the slope exactly in the middle. Okay. However, if you look at that, so we're gonna solve it making that assumption, and it should reveal some problem later on, okay? So, if I assume I have one interval delta x, but if I want to say, well, the slope at this point is the difference of values of the derivative using the two neighbors. So I have to divide now by 2 times delta x, because if this is delta x, that is also delta x, so I have 2 delta x, correct? So if I were to do that, I would then define my variable. So if I assume that k is constant, I can keep it out of the equation. And the first, so I have the difference in theta in time over delta t is equal to the difference in my gradients. My gradients are between I plus 2 and I minus 2. And the two are over 2 delta x. So if I take the common denominator, I have 4 delta x squared. And I have a term in terms of 2hi plus 1 minus 2hi plus hi minus 2. And that looks nice. So now I can predict the delta t at the future time. Okay. And the nice thing is that at steady state, I can also say that the change of water content is equal to 0, right? When I'm at steady state, I know that I will have as much water coming in as leaving at any given time. So the volume of water, delta change of water content is equal to 0, which means that that entire term will also be equal to 0. And from that, we can simplify and find that hi plus 2 minus 2hi plus hi minus 2 equals to 0. Okay. And from that, we can say that we have this. Right? At steady state, we could assume that we have the equivalence between points. Okay. Now, okay, so let's try to see if we can get a solution to this thing, right? And how it will work. And so we assume that we have a uniform soil specimen that is 30 centimeters long. We have a head of whatever, it's 5 to 1, whatever head is at so it doesn't say how frequently to make the increments, but let's make them at 1 centimeter. So we'll have here X. We'll start at 0 until 30. Sorry. I almost did it by pure coincidence. So here we have H. Now, there's different ways we could go about solving this. We can make a matrix and solve everything at once. We may have a look at how that would be done later, but it would require a 30 by 30 matrix. So you may not want to do that. So if you have well, let's see how we would solve it by hand. So if I have a matrix, let's look at something that is much simpler. And we said that H is 0. Let's assume that we only have 4 points. So H0 we said was 5. Say that H1 is unknown, H2 is unknown, H3 is unknown, H4, that was at the other end was 1. Okay, that's what we considered. So if I were to consider this, then let's see. I know. Well, okay. Right now, I think I'm going to skip this explanation. We're going to go with the step-by-step one, and then because this one makes some assumptions that it will be easier to see if we don't do it. So we said it's 5 at the beginning. So the boundary conditions, now we're putting boundary conditions. Our boundary conditions here are constant head at the inlet and at the outlet. Okay. Remember that in our equation, we were skipping 2 nodes. That's why I'm not finishing that little matrix. I just realized that I was going to hit a problem with the matrix because it would need too many members. But I want to highlight another problem. So this is solvable this way. So this is our initial condition. We'll call H0. So we're still trying to find steady state value, but we are going to make guesses and then fix the guesses until we reach a steady state condition. So for our guesses, we're going to assume that the value here, say it's 5 everywhere except at the boundary. At the second boundary, okay? So if I were to use this as a condition, let me save this just in case something happens and the program crashes. Find a different method. 0, 1. So what did we say? We said that the point was equal to so the basically at any node, we're looking at the average of not of the neighbors. This says to keep the central difference. This doesn't look at the neighbors for some reason. It looks to beyond because we started with, you remember why we look to beyond? Because it's a double difference, right? We find the difference of the difference, right? And because of that, we ended up with, I'm not sure it's clear, so let's go back to our figure. So I said that dH over dx is this over that. But I'm looking at the second, so this gives me the Darcy flux in one. This gives me the Darcy flux in the next one, and the difference in the Darcy fluxes gave me the final value. That's why the Darcy flux of this one minus the Darcy, so the Darcy flux of this one would be depending on these two nodes. Because we're looking at the central difference. That's why we skipped one, we were two away. Because here. So it's here, see? This is the first Darcy flux. It's two consecutive, sorry, that's +2 already, so. I skipped a step. Uh, +1 -1. Yeah, because we want to go to +1 and -1, right? So if I go here. So it's. The HI is not here, it's HI +1, and this is HI -1, so HI is not in here because I'm trying to do the central difference, that's why I have 2 times delta X. So if I move that +1, +2, it skips +1, it goes to HI. Right, that's why we skip +1 on this one, we have +2 and it has HI, this has HI -2, because I was trying to do that central difference centered there. We're gonna see why that causes problem if we were to do it that way and why we don't do it that way. But let's try to solve it first. So. Go back to this and we say HI is equal to the average, not of the neighbors, but of the neighbors +1. Okay. So first iteration, so we're gonna go iteration 1, iteration 2, this is it. Let's put. I pressed the control something and I don't remember what I pressed. Oh, formula, control. Sometimes you think by accident and then. Don't even know what I pressed. It's terrible. Press it and I don't know what it is. Okay, so we just want these to be labeled as iteration. You know what it means. Okay, so here at the boundaries are controlled. So even when we're doing it this way, at the boundaries, we will always have the same value. I'll just say that makes it boundary. There's different boundary conditions, but one of them is constant value like this. So here I would say is equal to the average of this plus not the following one, but the following ones. That should be B. Okay. And maybe I should start at 3 here, just so that it's easier to see that it's actually doing something. I mean, you would end up seeing it, but let's start like this. Okay. The problem is, first of all, you see here that this first point here already has nothing, right? So what am I going to put here, right? For the midpoint. So already I have a problem here. Furthermore, let's say that I put 3 here just for fun. And 3 here just for fun too. Then what happens to the other ones? If I were to copy the whole thing. Do a few more iterations just to see it. And we should start seeing the problem very easily. Let's start plotting. So we see that we get, steps along the way. Eventually it will go towards a value. Okay? But, so we see that it starts from essentially a straight line, and then we're finding at each step, it's changing towards a value that is slightly different, okay? But you notice that it's going up and down and up and down and up and down, and that middle value there stays at 3, which is not really what we want, and both ends seem to be completely separate from each other, right? You have this zigzag here. Okay? So that business of skipping a value doesn't work, okay? But how could I express the same? How could I express, and I have some slides here missing to explain that. So how could I express the same thing that I have here with a central difference, but in a correct way? Well, the central difference we have and this is how we express the central difference, right? And we had 2 delta x because we were skipping a node, right? We were saying the difference between to find the gradient, I was looking forward and I was looking backward. But the problem is that by doing that, we're skipping a node. We cannot have that in practice because you saw the problems that it causes. We have to assume a value for the 3, and then that becomes another boundary. So what do we do really? It doesn't work. So what we really have to do is say, okay, what if I wanted this to be 2 consecutive nodes? The only way to do that would be that my central point, if I do a central difference, it's really the hydraulic flux, the flux Q is at the midpoint between 2 points. Okay? In that case, so instead of being xi plus 1, xi minus 1, I could say, well, it's at xi plus half. And the other one is at xi minus half. So the delta x is still delta x is still one. Okay, it's not two delta x, the difference between the two values, it's still one. And conceptually, so this becomes delta x. This is at I plus one and I, or plus half if you want. But then I do the difference of the difference. So plus half. So where I have plus two becomes plus one. And I still have the point, the value at HI is still central. Right? So if this is point plus point half, 0.5, I plus 0.5 and I minus 0.5, by the time I get to this expression here, because now this term is in the middle and that term is on the other middle, this becomes HI plus one minus HI minus HI minus one. Okay? And this becomes delta x, this becomes delta x, and this is also delta x. So this entire thing is really the average of the two neighbors. Right? And you will see how that fixes everything. So I need to fix those slides the way they explain things. I think they're a bit more confusing, but I wanted to show to you if you were to go do the central difference and apply it in a strict way, you end up with that two delta x term there, but it causes problems when you try to solve things, okay? You cannot really solve it. So, and I find it's really important to see it, how to do it incorrectly, because intuitively, right? When people tell you about the central difference approach, your first tendency is to make the central difference from the point and the two neighbors. But once you go to the second difference, you end up having twice the interval. And that means you're skipping a point at some in that calculation. Okay, so I wanted to make sure I showed you how to do it incorrectly because it happens. It's a natural tendency when you try to do your own implementation, and it may lead you to a lot of not that they've ever happened to me at any point in my history, but it may lead you to wondering what you're doing wrong. Okay, because you're thinking you're implementing the half difference. So the idea conceptually is to be in the middle, and it makes sense. If I have 2 points, and think of it, if I want to evaluate hydraulic conductivity between these 2 points, where am I going to evaluate the hydraulic conductivity? At one point, at the other? I'm going to go in between, right? So I'm going to look at the hydraulic conductivity at I plus 5 or minus 5. Right? I'm going to look at in between the two nodes. That's the hydraulic conductivity that governs the transit. Yes.
So if you were to read a value for the hydraulic conductivity, are you getting the midpoint assigned to that point, or is basically the average?
That's what you should, it will depend on how you handle files and so on, but yes, hydraulic conductivity is really in the midpoint, in the interval. Okay? And it does become complicated when you have difference in K in the X direction and the Y direction and where it belongs to what. So we'll see when we start getting in 2D how we handle it. In 1D, it's not a big deal. It's fairly easy to handle. It's more of an issue in 2D because now you have sorry, I was already there. When you consider 2D, let's make ourselves sorry. I think it's better to go with squares. So if you look at your nodes. If you look at your nodes. We have so we have a bunch of nodes here. Hydraulic conductivity in the x direction. Well, if I look between say this node and that node, hydraulic conductivity is there, so it will be the average of these two. But if I look in the vertical direction, it will be, so in the vertical direction, say between these two nodes, so the hydraulic conductivity there is the average between these two. And on the other side, the average between these two. So you have to average kind of different directions opposite to the direction of flow. So it does take a little bit of mental gymnastics. Of course, if you have enough points, your grid is fine enough, you may decide, well, I'm assigning to this point the average of all the squares around it. And it should not be too far off, and that's one strategy to keep your sanity. But yes, when you get into 2D realm, you start having to start figuring out how your mesh is connected. But yeah, so if you were, I mean, if each hydraulic conductivity is shown by a different color. Okay. And again, in one direction or the other, so you start to have to do gymnastics there to figure out which two nodes and which, because the nodes are at the boundary. So if you want to find in this direction, you're looking at this boundary, so it's the average of these two, but in this direction, you're there, so it's at this boundary, so it's the average between these two and the average between these two on the other side, so. Yeah, it's but I think this does illustrate that it's at the midpoint, that's why it's +5, the hydraulic conductivity is evaluated at +5, so the gradient is between these two points. Okay, so we'll take this equation and just say instead of I +2 and I -2, it's -1 and +1, okay? And so if we do that, let's see how it fixes our problem. So now the boundaries are still the same. But, let's start from there. I mean, I should have put the X on the, ideally, the things that will move the most, you put them as rows. And what is more limited in space, you would put it on the, as columns. So I should have put my X on the next column, but it will work anyways. We won't do that many iterations that it will make a real difference. Oops. Let us freeze row columns. These, I made a boo-boo. Oh, I did not start from the proper area. Sorry about that. Oh, yes. That's what I did. I see my problem. I oh, better. Right. So now if I have the same iteration plot, what we notice is that we don't have those zigzags anymore. Okay? So it's more continuous and it's going towards something. What does it go towards? We don't know yet. So let's keep, here I should have the iteration number actually. Iteration 14. Oof, much? It's too much? Too much. Yep, it was too much. Fortunately for us, I thought about saving it. I thought of cover. We crushed a little bit. That's okay. See how you know you're live. Okay. Oh, I'm not on the correct screen then. Sorry. Goes there. There. Okay. Better? So let me, I will add here a column with the last iteration. And, or uh, we'll just count from there to the end. Set of C1, 0, 0 with one row and say one. Want to find the maximum iteration. I want to automatically find the proper iteration. And so this one we have offset of this cell. No offset row wise. And this offset column wise, one item. So that's the last iteration. Okay, this is a special column that shows you iteration 99. And if I were to continue this, okay, now it's iteration 107. So I just have a magic one so that the first one, the reason I want the first column to be that is because I can add that one to my chart. I just need to add one the range. Data range, let's see, B. Ranges, data series. It's the same. The Y will be B. Okay, so you can see the more and more. So if I were to Convert to, so it's starting like this. And each series I add, it goes towards a potential solution, but I know that the solution, I iterate and ideally I should be approaching my final solution. See that last curve? Only takes that last curve starts moving and just when it stops moving is when I know, see, it's looking more and more that it's gonna become a straight line, which makes sense. Because that's what I would expect, right? It's a gradient, it's a single gradient, single soil. So I would not expect there to be a difference. So it's still not quite straight, but you can see that it's coming. So this is one way of finding my solution. Step by step. Okay? And I could evaluate my errors, my changes between two consecutive, and I get a straight line, which is my expected solution. And that's why I have that column be the last, so I don't have to change the graph every time. Okay, that last one is always plotted there. Okay. Now, what difference does it make? What my initial value was? That's one thing that you can, so it took me how many iterations? I'm 155 iterations right now, right? I started at 3 because it was the average between the two values that I had there, 5 and 1. So the average is 3. Let's say that I started at for my first guess in between at 0 everywhere. What would it have done? So after 155 iterations, I'm nowhere near my straight line yet. Okay, so yes, your initial guess will affect how fast it converges. And that's what you get with so it would have taken many more iterations to get to the final value. That's something there. So that does it for this first. Now, one thing that I wanted to show before, like if we start from this idea that I have H0 is 5, H1, H2, H3, H4, and this is 1. So I'm making bigger steps. I just wanted to see what I would get in between. Could I, because this is steady state, could I solve it at once? This is unknown. Obviously, these are unknown. Well, I know that H0 equal to 5, H1. But I also know that minus 0.5 times H0 plus H1 minus 0.5 times H2 0, right? Because this is my steady state condition, right? H1 is equal 1/2 of H0 plus H2, correct? Let's say that H1 equal 1/2 times H0 plus H2. Okay. And because I can say that minus 0.5 H0 plus 0 plus H1 minus 0.5 H2 equals 0 minus 0.5 H1 plus H2 minus 0.5 H3 equals 0 minus 0.5 H2 plus H3 minus 0.45 H4 0 and H4 equal 1. Correct? These are things that I can say. So if I put them in terms of 0, 1, 2, 3, 4 in terms of index, okay, I have H, and here I have a vector. This one is H0, H1, H2, H3, H4. So I have 1 times H0. That would be equal to we said 5, 1, and 0, 0, 0. If you put things in matrix, you have minus 3.5, 1, minus 3.5. Don't panic, it's just because of the font and size. And that will be 0, 0. Then we have 0. Yeah, I should. This is not part of the matrix, so let's keep it above. We have 0 minus 0.5, 1 minus 0.5, 1. Sorry, 0. Why did I say 1? 0, 0 minus 0.5, 1 minus 0.5, 0, 0, 0, 0, 1. Okay. So if I wanted to find the solution of this, I would have to invert this matrix. Call this matrix. And if I invert my matrix and I multiply by letter S. S. So M inverse of my inverse matrix. This is I'm going to invert this and multiply by that. I will get I will get 5, 4, 3, 2, 1. It makes sense if those are equidistant. Let's see that I have a straight line between. It's a logical solution. So I could express everything in terms of matrix and solve it at once. Now, here I only had 4 nodes because it was easier to visualize and we could write, but it would work with the 30 nodes. Okay, if I go from 0 and then I go to 30 and I say it's 1, at 0 it's 1, and at 30 it's 1, I would have to write my matrix with zeros everywhere. But you can start to see how it's a bit more tedious to write that. That's where a little bit of coding comes in handy to fill these things. It becomes a bit tedious to do. I mean, you could do it on a spreadsheet too. By checking the row and column and deciding on the indices, so you can generate that 30 by 30 matrix. Already you're talking 30 by 30. The advantage is that you solve it in one step. Bam. Even on a spreadsheet, I could have, what I did with all these steps that I needed ever more steps, every time more and more and more and more and more steps, I could have solved it in one single giant step. So you can't do this matrix wise in one step. So the steady state, there are 2 ways to solve it. With matrix, bam, once. And if you're using Octave, that's the method I recommend as much as possible if you're using MATLAB or Octave, because they're optimized to solve for matrices. Although, well, you don't know how many steps it would take, and they're just not as optimized for groups. Okay? So if there's a way to express the same equations as matrices, go ahead and do it, and then you will be able to solve it. Okay? So let's take a quick break on this. And then when we come back from the break, we'll see what happens when we have more than one material, because the whole point of doing these numerical methods is to solve it, because this straight line, you don't need a computer to solve it for you, you know what I mean? So the real beauty of it is when we add materials. So after the break, we'll look at it, and then we can run home. And we'll be done. Oh, I forgot to check the chat today. Sorry, guys. Let's see if there was a question. Oh, I'm sorry, guys. Ah, there was no question. I feel better now. I'm not used to having had the chat in the past few days. There was no one connected, so you lose the habit. Okay. I'll be back in a few. By the way, people in chat, I may sometimes forget to look at the chat window. It doesn't show up unless I put it on. So if you have a question, you see that I'm not answering, feel free to turn on your mic and ask the question, okay? Don't be afraid to interrupt me. I'd rather address your question when you have it than figure out half an hour later that you had a question and I never saw it, okay? Let's continue straight. Stay away. So as we saw, skipping an index was not a solution. It was just making little steps, causing all sorts of trouble and not leading to a solution. So that's why we use the I+5 and I-5. Okay, conceptually, and that way we solve properly. Now, what happened when K is not uniform though? Well, if we solve for the same equation as before, we start. Okay, so here, by the way, I put as a super exponent, that's not a power, this is just the index in time. Just to show that it's separated from the index in space, because eventually we get to 2D, 3D, so we end up 3 indices in space. So it's just a way that sometimes people will represent the index in time, that it's not a power. So the n+1 is at time n+1, time n. Or not necessarily in time, but in this case, in terms of iterations. So we have minus k at in the midpoint, so at I plus 0.5, and again, there's a real reason why it's 0.5. We're in that square there, in the midpoint of that square, represents the interval between two nodes. And it really is where you evaluate the hydraulic conductivity. Minus K at I minus 0.5. So you see here, because K is changing, it's now important to not keep it outside. It's no longer a constant that you can keep outside. You have to put it in the operator. And now if you distribute it inside your operator, so you just multiply this by H plus 1 minus this. The delta X can come because it's a constant delta X, we're still keeping the constant value. And now we end up with this term. If you regroup what's as HI minus 1 and HI plus 1 here, see that they go with their own individual K index minus, and now you have the sum of the two Ks times the H in the middle. So if the two values are the same, that becomes 1 plus 1. So later on, when you isolate I, you divide by 2. So you see that's where the 2 came, okay? And so if you simplify everything and you assume that you have a steady state condition. Again, today we're just looking at steady state condition. Time dependent will come next week. Okay? So for for steady state conditions, we get K I plus 0.5, K I minus 0.5 at H I plus 1, H I minus 1. Divided by the sum of the K's. Okay, so it's simple, the sum product of the neighbors, basically divided by the sum. And so it's a weighted average. So when you have a constant value, it's a straight up average. When you have variable K, it's a weighted average. To get to steady state. And you can do it again, you can do it at once. We'll do it both ways just to see how fun it is. And we'll do it with multiple steps. So we'll add a value for K. We don't necessarily need the legend. And so let's find K. So what's the example that we're giving? Oh, they're not have exact, okay. So we have a centimeter, it's again 30 centimeter long, the head is 5, and the toe is 1. Then we have, it's divided in 3/3. 0.001 meter per second between 0 and 10 centimeters. 0.005 between 10 and 20, and 0.001 again between so it's basically 151. And the reason why I can just ignore the units is I just need to keep them in the side because it's steady state. So I'm not looking for the exact time that it takes. I just need to know the relative size of each. So it's much higher hydraulic conductivity in the central part than in the others. So let's see how that looks like when we try to solve for it. That's why. Fine. So that was the original solution when we had constant value. So let's see what it looks like when we have a hydraulic conductivity that changes. So we said as long as I'm gonna put an equation there if you don't mind. Okay, so if the average of this and that is smaller than, we said, 10. 10 is 1. Else, if average of A4 and A2 is smaller than 20. And we use a 5. Else 1. That avoids having to look at things individually. So between 9 and 10 is 1, between 10 and 11 it's 5. So I have properly denotated all the values. You notice that I left us, I skipped a line between my values. I like when I work on spreadsheet very often. It's not always practical, but possible. Separate what happens at the nodes and what happens in between the nodes. So these are the nodes, this is in between the nodes, and visually I have it. So in some cases, it will avoid by making mistakes that can be avoided. So what will change in this particular case? So iteration 0, nothing changes. I'm gonna still assume 3 everywhere as my starting point. What changes is that I now have a weighted average. So it will be a weighted average of the so the previous K, and I will fix the column B times the previous IT plus, and this is another reason why it's convenient to leave a gap. When you don't leave a gap, you now have 2 consecutive items compared to 2 items that skip one. You know what I mean? That minus and plus, but if I didn't leave a gap, it would be direct row. So it's easier to make a silly mistake like that. Sometimes it becomes impossible to do it this way, right? When you have big data sets and you want to be able to make matrices, it becomes a little bit more cumbersome, but when possible, we do it this way. So plus, now we go to the next one. Fix the B times 6. The previous item. Well, I go C, I should have been D. Not C, but D. Okay. Don't panic, we just done the first one. It's kind of neat, the shape we're getting. Oh, I forgot to divide, sorry guys. I forgot to divide by the sum. You did that, right? Yeah, boy. I knew you knew it too. Yeah, everybody knew everything. Okay. So now we that times that plus that divided by Copy. Okay, that looks better. And what we're getting as our final value seems to be three straight lines, which makes sense. That's what we expect, right? And with different slates, of course, we have less head loss in the middle, which has a higher hydraulic conductivity, which is also what we expected. These are things you could have done by hand, of course, in 1D. You could have found the ratio, found the slopes, the equivalent slopes, and you could have solved it by hand. Again, if we started with the initial values which were different, say 5, it would have taken many more iterations to get even close to our. So it always, when in doubt, when you have two boundary condition, what we're learning from this is that to speed up the iterations, we start as an initial guess with the average. Okay, this is what these little experiments are showing. We started with the average, which is 3 as our initial, as a first guess in between everywhere. You see, we converge much faster. We were nowhere close to convergence. Then we would have had to go at least twice that much, right? So it's important to know when to use the proper or what value. I mean, the values that you choose will have a huge impact on your sets. Now, could we have done something like this, and what happens if I have, say, if my hydraulic conductivity here, say I had a different value for the last one, okay? Okay, so it still works. So if I had used 3 here, I mean, I'm still a bit away from my convergence. It looks a little bit curvy, but we're getting there, right? We have 3 different slopes in this particular case. So, so what would it look like if we were to try to solve this in a matrixy way? Gonna try it. Let's see if we can do it. Oops. Okay. So in the matrixy way, what would we have? Well, let's do it for a small small size. So we have index 0. Again, the intervals will be equal, but it's important to know where we are. This is 0. This is so it's be the actual x, and this is the index. You're gonna start with a small value. So again, like we did before, and solve quick. So here we wanted to say we had 5. 0, 0, 0, 1, because at the boundary we have what we're going to say is H0 equal 5. H, and then we have minus 0.5 H. 0, is it minus? No, it's minus A1. Here I'm going to the index of the k's, like starting at 1 instead of starting at 0 because they're intermediate. So you can see how it starts getting messy when you start, or if I have an index k0 and I keep them without offsetting them, let's do it this way. It's k0 minus k0 times, because let's look at it this way. The nodes are numbered 0, 1, 2, 3, 4. Okay, node, and the k node would be 0 in between. Okay, I'll put that on this side. So it's important to sometimes just do things to visualize before you start programming things, right? This one will be 1, 2, 3. Okay, 0, 1, 2, 3 will be the k's, and 0, 1, 2, 3, 4 will be the nodes. There's one less k than there are nodes. Okay? Because the k's are in between two consecutive nodes. That's why I was leaving here the gap, okay? To avoid confusing myself. Okay? Actually, another thing I like to do, I did not do it this time, but one thing I commonly like to do is have conditional formatting. Formula is then row, then I create style. Let's say background. Saturation 50%. Let me create the style first and out of the format. Additional. Can you see it on screen? It's a bit subtle. Yeah, it's too subtle for the screen. Let me change that. Uh, that better? No. It should be visible. It is indeed visible. Okay, so if you do a conditional formatting like this, it lets you more easily know where to expect the thing. So you can see that I have my values for my k in between the nodes, and all the other calculations are the nodes. So, but if we're trying to do things in the matrix way, we cannot use that. So we'll have to see two consecutive values are in between. So let's keep that in mind, okay? So. Here you see the back one is the same K as the previous one. And the next one is one less. The K node index is one less than the value. So if I have here my Ks, K will be in between. And again, I can say if the X is smaller than 10, 1, else if X is smaller than 20.5, else if 1. We have only one K in this particular case where we use 5, all the others are using 1. Okay, and we're looking at the back. Okay, so let's call this MK. Call these MY. So here we have what? What do we have in terms of index? We have 1. So the diagonals is all ones, always. In this particular case, we have zeros for the other values. Okay. And then where it changes now is for the back. So here I'm going to use we're going to go to the MK before all the time. So now we're fixing the row. It's on row 10, the MK 74. Divided by, so it will be, because if we look at the equation, go back. So this is equal to, so this is 1 minus this over that, so it's Ki plus 5 divided by the sum, and the other one is minus Ki minus 5 divided by the sum. Okay. So we will have a minus. Yes, it should be negative minus this divided by this K. Well, R plus this one. And the next one will be minus this one divided by the sum of the same two. So when both are equal, it's minus 0.5, like it was before. And look, this is a diagonal, so I can basically paste it in both of these. So I need to just fill everything else with zeros. Okay, so this is my matrix here now. So we call that matrix, let's call this matrix B for variable. And this is still S, so. Here it's inverse. If I multiply both of these. Okay, so that gives me a certain distribution. And let's see what it looks like. I mean, there's very few points here, so it's not gonna be pretty, but can try again with more points after. This is the pressure head, yes. So here we say transpose of X. For fun, let's see what it plots as. So it looks general neighborhood samey. The problem is, of course, that we only have go to a quarter, so it's the spacing is uneven, doesn't match the boundaries that I had, which was at 10 and 4. So to do this properly now, I would have to do it 30 by 30. So you want to try 30 by 30? Oh, somebody looks so convinced that we can do it. I feel all puffed up and confident in myself. Challenge accepted.
Go for it.
You're not gonna try with me?
Oh.
Let's see if you can beat me and then you can come and show us all how it's done. You can show us all how it's done. No? Okay. I'm the only one that has a 5-year-old around, make him watch trendy movies. Huh?
Me too.
You haven't had to watch that one?
Trendy movies.
Okay, when I said done, didn't ring a bell?
Don't think.
How old and boy or girl?
5 girl.
And you don't know what done is about?
One Piece.
Hip Hop Demon Hunter.
Oh my god.
I mean, that's how the movie's done. I'll show you how it's done. I've watched that movie so many times by now. Uh, No, I haven't seen One Piece, yeah. It was trendy, what, 2 years ago?
What? I guess today too.
No, it depends. For anime fans, it may have been 20 years.
Yeah.
For normies, it's 2 years ago when it came on Netflix as a
Yeah.
live action, right?
Yeah.
So that's when I heard of it. I had never even heard of the One Piece before. And now I haven't seen it, but I've heard of it. I guess you're an anime fan then.
A little bit.
Okay. Okay, so let's see. Now we're going to have our same thing. We'll have our Ks. We'll have our, okay, let's have index. We'll have X every centimeter. Yeah, so X will meet, will match index now. There. Okay, and we'll have K, which will go, we'll keep the index starting at 0 there, just because that's how you start your indices in most programming languages. That's just going to be that. Which is convenient. I'll keep a row for X separate from index because sometimes you could have fractions and K will go, we'll stop at 29. It was actually only 30. So 30 intervals because we start at 0. And I mean, if I were to offset by 1, if I start at 1, then it's 1 to 30, which is what K really is. And so we'll have here our obviously own index. X. On K. So K, I'm gonna change that. Sorry. Because K, we don't want to have this weird thing here. For K, we want to say if X is smaller than 0.1, 1, else if K is smaller than 0.2, 5, else it's 1. That doesn't sound good. Oh, let's say 0.1. We were going centimeters there and I. Sorry. And it's late for everyone. I can count, I promise. And count to 10 at least. That looks better. See, that's one advantage of a spreadsheet. Doing this on a spreadsheet, you may make the same mistake in code and not figure it out. This, because you see all the numbers on the spread like that, and it can be easy to catch. But sometimes it can be hard. So, I'll be honest that way. Sir? Okay, so the idea was that let's fill everything with zeros. It'll be easier. And you have this many. This many rows and columns. Sometimes it's just easier to initialize everything. And now we take care of our diagonal. So other advantage of 1D, we only have the central diagonal. You start having 2D and you can have geometry that changes. You start having sparse matrix. It's no longer a diagonal matrix, it's a sparse matrix. Okay? So be aware of that. The matrix will change shape. And because now, in terms of nodes, you have to put every node in a sequence. Yeah, it's a continuous sequence. You're no longer looking at X and Y nodes. It's a continuous sequence. So this node is now connected to above, which is several nodes before, because you have to go the whole previous row and the node below, which is a full row after, and then so it's conceptually, so it messes up the distribution. So that's where, coding for that. Setting up the matrix is what the user interface is all about, right? To simplify that. Now, if you know exactly where you put things and so on, you can manually build your own. But otherwise, building matrices, that's why the way we did it before, without a matrix, okay, this is the simplest way to solve these problems. You need many more iterations, but the advantage is that particularly when you're starting working in 2D, you don't need to figure out the relations between things. Still possible to do, but it's a bit more complicated. You need more steps and more spreadsheets. Okay, so now our vector, solution vector was what? 5 for the initial node and 1, right? And we're gonna have 0 everywhere else. It's gonna be the inverse of this times this vector. That will give us the solution, okay? This is our boundary condition setup. And so we had here 1. This one was here 1. And so here what we will have is equal to the k before divided by the sum of 2 consecutive k's, right? That's a minus. And then we have 1. Then we have the k after. Again, we fix the row divided by the sum. Sum of those two. So we can do it manually or we can do it automatically by having conditional statement. Which one you want us to try to do? Conditional statement, okay. Okay, so what we can say is if the index here, so we fix the row. Yes. Okay. So we can say if this index with a fixed row is equal to this index with fixed column, then it's 1. Else, if this with a fixed row is equal to this one with a fixed column -1, then we say that it's this minus B3. So the first one divided by a sum of the two consecutive ones. Else, if this with a fixed row is equal to this one with a fixed column plus 1, then it's the next one. So instead of C, else it's 0. Yay, looks like we got it. Oops. Got it. Oh, by 0, 1. Let's see if you guys skip one.
Is it no subset right now? So you might have to. Over it, yeah.
Yeah, but we're supposed to finish one less, right?
But we're finishing on 30, not 20.
Oh, yeah, I got that. Yeah. That's cool. No, wait. So we have intervals, so this is. Yeah, we're supposed to two consecutive, right? Oh. I'm advancing with I'm supposed to be advancing with the. See, this is still supposed to be. It's a 1. Okay. I should have Because I'm comparing to the left one. What's the problem is, right? I think the easiest thing to do here. Try to insert a column, and that's why I don't follow before. So instead of being the K from there that I'm supposed to take, it's the Ks. So I compare the row to the row. And then here, instead of being C3, it's this. Not, it's. Oh, it could say A, I meant B. In this case, it's. Yeah, because for each row that I go down, the two Ks should be the same. But here they were moving with each column. Right? That's what caused that trouble. Okay, that stays the same. This one is close. Last row, say from 0, except. That's supposed to. Yeah. That's better, right? It's called this long S. And this one will be the long matrix. So if I do mult and inverse. Okay. Long matrix. Long S. And here I have long X. Oh, sorry. Transpose long X. No, I want one series. It chose the wrong digit type. XY scatter.
Zero, say.
We did it here, 5. 5, 4, 1, that was fine. This one was for you. Put it in the wrong.
Or else in your case, not always, always.
Great, what's like your boundary condition?
It's supposed to be 1. Oh, it's not 1 and 5, it's is it 5 and 1?
Yes, yes.
Yeah. Okay. So it goes from 5 to 1. Why I get minus values here?
Zero.
Okay, at 10 we have a boundary, so at 10.
It's not symmetrical thing.
No, because we have that's where we have the changes. At 20, we should also have something. Yeah, we have changes in both sides. And That's 318. Oh, 318. Okay, this is a see a mistake here. B8 plus B9. B8 plus P9. Ah, one step.
What exactly?
Yeah, it was, you see that? I saw that both on the same color.
Oh, okay.
It was, but I put B9 plus B9 rather than. So in one step can be done. Using, so it doesn't need to be little iterations and checking if you have, so that's much more procedures, but it can also be done one go, okay? So it's not because we use finite difference that we were doing it step by step, it's just one way that we can use it. In finite element, you basically only have for solving steady state, this is the only way to do it. In finite difference, you have options. So the other method saves complexity of treatment. It's a simpler equation, but you compensate by having to have many more like it's more time consuming, but will use much less RAM. And as you can see, it has less chance of making a silly mistake. So it gives you a backup tech also. But it progresses eventually. But this is the purest finite difference, for instance. If you go by going to solve a steady state problem by finite difference, numerically, typically, this is how you would do it in one step for steady state. But the other one is inspired by the time dependent problem that we're gonna see next week and so on. And the only difference is now then the values of the dimensions. Today, we're only caring about the ratio between the various k values, right? As long as it's the same units, this is one, this is five, this is one, it's good enough. But when you look at time dependency, now you need to know, okay, this is 0.001 meter square per second or something like that. Okay, so I'll save this and upload it with the files for today, in case you want to have a look at it. But this is the kind of thing that good. So this gives you a taste for how I like to do this course. So it's less of a theoretical, more of a hands-on, try to get things to work so that hopefully you are less intimidated in the future by numerical methods, right? We can solve it. It's only, so this was 1D. So the challenge will be, we'll go into 2D. First, it will be 2D with rectangular domains. Then the fun part, 2D with non-rectangular domains. Oh, that's when the fun starts. And you can solve it on the spreadsheet with the help of a few tools like, well, mostly one tool that is called LibreCAD. It's a handy one. I have to make sure it still has its Pixmac export. So notice that they dropped it from LibreOffice. It's sad because it's a very powerful export form. Okay. Any chat questions? No chat questions. Any questions? A fun time?
I'm just gonna go home this weekend and try to redo what you did.
Yeah, I'll upload the spreadsheet and so that you can have a look at it. Let me do it right now before I close the for FTM. Modules. Pictures. Desktop.
So next week is the 2D steady state version of this.
We're gonna start with 1D. No, oh yeah, next week 2D steady state. Yeah, sorry, steady state. Yeah, the time dependent one is gonna come later. Or 2D steady state. We're not gonna do the matrix one. It's doable also. You just have to figure out where the nodes are. I mean, well, if we have time, we'll see. But you can see that now it becomes more difficult to know this node, but it's no longer a diagonal,
Yeah.
right? So, it is more challenging. It's possible to do. You need an extra sheet just to be able to identify the node count. You say if node, then this node, and then you can see next neighbor, a sheet to identify neighbors and the node ID of the neighbors. And now if this is so it becomes messy real quick. It's something that is easier to do programmatically sometimes than on a spreadsheet, but I'll try, if I have time, I'll try to figure out how to set it up and do it, but we'll definitely do it the first way we saw today.
In a program, if you program it, you just have to see like the operator and then the size of the matrix and then.
Yeah. Yeah, it's some things are easier to do once you know how to program a little bit, and it's worth checking, but yeah, it's doable too. I found in the past a few strategies to do it on a spreadsheet. I haven't really been presenting them because it gets a bit heavy on the spreadsheets. Sometimes it's a challenge that is fun to do. Like what you can do on the spreadsheet when you select the groups for the presentation there, the topic.
I think it's good because this for me, when I was doing my master in hydraulics, we never did Excel sheets, but they would show us the basic functions for doing like Newton-Raphson and stuff like that. Newton-Raphson is basically finite difference, but you find the roots of either a cubic or whatever. But the problem with that is it's fine because it's 1D backwater and it's hydraulics and stuff like that, but you can't do it in 3D space. And if you can't do it if you can't see the big matrix, you can't see where things can go wrong. But at the same time, if you're always working in 1D, you're not thinking about how to optimize your matrix or to optimize your computational resources. And so for me, coming into a course like this, I say, oh, I can just solve any ODE with time series, but then you set up the matrix the right way and you show us, and then it's easy to understand so that when you go back and.
Yeah. Setting up the matrix is the fun part, right?
Yeah.
Because you can see once you do it in 2D, now you have to identify nodes. Particularly if it's a rectangle, it's not too bad. It's only at the edges that, I mean, the up and down neighbors in a rectangle will always be a fixed count away. But once you start going to a domain that is not rectangular, so the neighbors are now a variable. It starts being challenging too. It's still doable, but it starts adding adding complexity. Yeah. But yeah, if when it's a rectangle mesh, you end up having a main diagonal and then equidistant, at the edges based on the domain, you have two other bands. It's a three band basically matrix. Okay. Other questions on chat? I mentioned, don't be shy to voice your questions if you're on chat and okay. So that we are sure not to miss any questions when they come. Okay, so if there are no questions, feel free to run home. Oh, it's later. And I hope we were finishing. So, but at least we did good. We did good. That was a pretty fun little nature setup there. Okay, so next week.
Professor, we'll talk about the material point method.